In this video, we will discuss a recursive greedy approach to solve the activity selection problem. Say, for example, we have an activity selection problem that looks like this. We have our resource here where the time duration for which the resource is available is from 0 through 7. We have 7 time slots available. And then we have 5 activities competing for this resource. And what we would like to do is maintain a list of start times and finish times for each of these activities. So the first activity A1 has a start time of 0 and finish time of 2. The second activity has a start time of 1 and finish time of 3, 1 and 3, and so on. We also want to create a variable n which maintains the number of activities we have. Now remember, the trick in greedy approach is to always select the activity that finishes first. So one of the really important things that we have to notice here is this is sorted by the finish time. And the trick in greedy approach, the trick is to select the activity that finishes first. Now, because of this, and since the activities are already sorted, it's obvious that we can always select the first activity sorted by the finish time. But then after that is the question. So ideally, what we want is, I want the set of all the activities that are mutually compatible, and also I want the maximum list. So my optimal solution is this set of activities which are mutually compatible, and also the size of this set is maximum possible. So say I create a method called recursive activity selector that can take as input the list of the start time, the list of the finish time, a marker for me to point from where to start solving the problem. Say I would at the beginning supply this to be 0 because I want this is the time from which the resource is available. And I also supply simply the list of the total number of items I have, n. So S would be my list here, F would be my list here, N would be 5. And since the resource is available from 0 time, I supply 0 as input. So we want this method to return us the optimal solution. This is the set of the maximum set of the mutually compatible activities. Now let us design this method, recursive activity selector, that takes S, F, and let's say this we keep dynamic using a variable called K, N as input. Now the first thing we want to do is, after this time K as input, which will initially be 0, we want to find the first activity after time point 0 that is compatible with all the previous activities. In this case, the previous activities are null, but we want to find the first activity that is compatible and that also has the minimum finish time. Now to scan through all the possible activities, I'm going to create a counter called M, which I set to K plus 1. This is because we know that the next activity that we select, given K, which now has, say, a finish time of 0, we can actually add another finish time here. This is F naught equals 0 to this list. Now we want to scan through all the activities that start after time equals to 0 and have finish time at least 1 plus the finish time of the current activity. So we're not going to look for any activities before that. So I'm going to create a counter that starts from K plus 1. And of course, we do not go beyond the list. So while M is less than N, I would like to keep scanning one item after the other. And we also want to check and make sure that the new activity has start time that is either same as the current finish time or more than that. That is, what we want is start time of this activity M should be more than or equals to the finish time of my previous activity, Fk. So this is what we want to meet as our condition. So in other words, I want to increase my M, that is keep scanning the elements, keep looking for elements until this happens. So while M is less than N, I would like to increase my counter, M plus equals to 1, and also until this happens, that is Sm should be less than Fk. So until this happens, I'm going to continue to increase my counter to find the next activity. So at the beginning, when K equals to 0, I will set M equals K plus 1. So my M is pointing to 1. Then I check, is M less than N, which is true. And then I check, is the start time of m less than the finish time of k? So finish time of k is 0. I check is the start time of m less than 0 or not. So the start time of m is 0. Is 0 less than 0? No. So we do not increase this counter. In other words, as soon as the first time slot is available, the first compatible activity we found is A1. So this serves as a technique for us to examine all the subsequent activities such that this new activity that we find is compatible with AK. Now, in order for this recursive method to terminate, we can actually add one more condition right after this line to say something like, if m is more than n, then we want to return empty set. So this code can go right after this line to terminate the recursive activity selector, so that we terminate the loop after we have k equals to n. So going back to our method, now that we have found the next activity that is compatible with ak, we would like to return this as a solution. So return am. So this is our solution. And then we want to add the solution, optimal solution, to the remaining activities. So I want to call the recursive activity selector again, passing s, f, and then this time I will skip all the activities that are incompatible and pass the next activity that we have selected, m and n, as the input. So now next time when we call this m equals 1, so once we call this function, we set m equals k plus 1. So here next time k comes in as 1. So m becomes 2. Then now m is pointing to 2. So we've already selected this activity as our first activity. And then we check, is the start time of S2 less than finish time of 1? So the start time of activity 2, is it less than the finish time of activity 1? And this is true. So then we increase m by 1. In other words, we're trying to skip the second activity because we found it incompatible. So then we increase m to 3 now, and we check, is the start time of activity 3 less than the finish time of activity 1? So the start time of activity 3 is 3, and the finish time of activity 1 is 2, and this 3 is not less than 2, so we do not increase m. So now m is equals to 3 now. In other words, we have selected activity A3 as the next compatible activity. So we at first had added A1 to this sum. Now we will add A3 to it, and then again call recursive activity selector with S, F, and m equals to 3, and so on. So this is how the recursive activity selector method works. Overall, this while loop only runs until it scans the activities linearly to find the next compatible activity. So even though this is a recursive call, the entire recursion, the main recursion, runs this m equals m plus 1 only n times. That is the size of our activity set. So the running time of our recursive activity selector algorithm is big theta of n.